equipment around a little bit to really refine what was going on. But it was so periodic that they actually called them LGMs initially for little green men, which was a fun thing, but it did show how periodic the signal really was. And it turns out that these pulses were coming from a spinning neutron star, rotating neutron star called a pulsar now. So there was this process sort of iterating over theory and observing. One of the notable things that happened that sort of cemented the view of this being a rotating neutron star was the fact that the Crab pulsar, its period was seen to be increasing, and we'll see why that is in a second. But that was a very telling thing to observe. So I always, oh, sorry, it's warning me that it's recording. I always do like to add this bit. Jocelyn Bell Burnell was snubbed for the Nobel Prize in favor of her advisor. It's a very unfortunate story. She never sort of expressed any real discontent over it, but you can read her account there. So yeah. Okay, so a very important point about these special neutron stars called pulsars, they don't actually pulse. They're more like lighthouses that are beaming radiation out of their magnetic axes, and they're spinning around such that if they're oriented in the proper way, their beam will sweep across your line of sight. And then you see that periodic rotation as a pulsating signal. They have relatively stable pulse periods. This depends a lot on kind of what part of the pulsar population they belong to. The ones that we're sort of interested in the pulsar timing array context are millisecond pulsars, and these are some of the most stable ones. You can learn sort of some useful information just by imposing some basic boundaries and kind of looking at how all of these measurables are related. I'm not going to go into the sort of derivations or anything because I don't think that's a lot of fun. But I will just say a couple of things. So if you just sort of impose the fact that centrifugal acceleration of the equator for this neutron star can't exceed gravitational acceleration, right? Then you see that you can do, just based on the period, a very quick calculation of the density of the source. And so we know that the fastest millisecond pulsar that we know of is something like, it's less than, I think it's more like 1.1 milliseconds. But anyway, that implies that the density has to be about 10 to the 14 gram per centimeter cubed. And that's something like the density of an atomic nucleus. So these, as expected, are really quite amazingly dense objects. We also know that most stars have approximately dipolar magnetic fields, and we know that as that collapse happens, the magnetic flux is conserved. And so pulsars end up having magnetic fields that are wildly strong, something like 10 to the 15 Gauss for sort of the most magnetic ones. Normal pulsars have magnetic fields of something like 10 to 12 Gauss, but the Earth has a magnetic field of half a Gauss. So it sort of puts things into perspective, I think. And we're going to simplify this sort of model of a pulsar and later the model of the emission mechanism. But the basic idea here is that you have a misaligned rotational axis and magnetic axis. And you can model it as a dipole, right? This pulsar is dipole. So as it rotates, the dipole radiation is extracting rotational energy from the pulsar, and so it causes it to spin down over time, slow down. And so one example of this is the fact that, or I guess one effect of this is that it's emitting a very, very low frequency radiation. This is not the radio emission that we're necessarily observing when we're doing pulsar timing. But this is what's sort of heating up the Crab Nebula, for example, and causing it to re-radiate sort of in this broad spectrum way. And as I said, the actual picture is a little more complicated. Okay, so you can calculate, assuming this dipole model and the fact that you're able to measure the spin down of the pulsar, you can calculate the spin down luminosity, the magnetic field strength, and interestingly, as you might expect, because we sort of know how quickly it's spinning down, the characteristic age of the source. And so we know that most pulsars are, sitting in the 10 to the 5, 10 to 10 years, so galactic type ages. One thing to note is that this characteristic age is often overestimated, because when these pulsars are very young, they'll go through a period of spinning down more quickly, and it's sort of it's just an estimate, but it's a good rule of thumb. Okay, so this is a very famous sort of a diagram in the pulsar world. It shows spin period derivative on the y-axis and the actual spin period on the x-axis. And it shows us that there are some different types of populations of pulsars that are actually interconnected in some ways. So you can also see that, I hope that it's clear enough, but anyway, there are these diagonal lines of increasing magnetic field strength going to the upper right, and of increasing age going to the upper left. Is that right? No, sorry, increasing age going to the bottom right. Anyway, so you have these very young, energetic pulsars with strong magnetic fields. They've sort of just been born. They're early in their pulsar days. You even have magnetars, which you've probably heard of in the very upper right of this diagram. Then you have sort of, as they evolve, they join this sort of normal pulsar population. And then most interesting to us is the fact that over time, these normal pulsars will become millisecond pulsars. And this is a little bit contrary to what your intuition might tell you, right? You would think that the most rapidly rotating neutron stars are going to be very young ones, right? Just fresh out of core collapse. But that is not the case, and we'll see why in a second. But we call this process of these pulsars, these millisecond pulsars getting spun up, recycling. And so during that process, the pulsar system gets circularized, right? They're usually in binaries. They have very stable orbits. They spin in a very stable way, and they're obviously spinning very quickly. There's also, other interesting populations here, like all these double neutron stars that are like partially recycled. Those tend to have really high eccentricity orbits, and they're really good for studies of GR, but not usually for pulsar timing arrays, so we won't dwell on them too much. Okay, so the recycling process, basically most millisecond pulsars are found in binaries, and they are going to accrete a bunch of matter from their stellar companion, right? And that accretion, just conservation of angular momentum, speeds them up to these extremely fast rotational rates, right? On the order of a millisecond, so sort of mind-blowing. During that process of accreting matter, there's actually a sort of strange plasma shielding effect, and it causes the magnetic field to weaken. So millisecond pulsars usually have magnetic fields on the order of like 10 to the 8 and 9 Gauss. And during the process, the binary also circularizes. So these are very non-eccentric binaries. And the last thing I'll say is that, there are some isolated millisecond pulsars, but we think that these are coming from either getting flung out of their orbit or from the pulsar ablating away the companion. And we actually see this in the form of what we call spider pulsars, which we won't get into either because there are very few of them timed as part of pulsar timing arrays, but they are very interesting systems. Okay, I'm really gonna skip through this quickly. Pulsar emission is sort of a notoriously complicated subject and sort of surprisingly poorly understood, but this is gonna be a very serious simplification. So, you have this magnetosphere that's the chargers are getting pulled out of the neutron star and sort of aligning themselves around such that you have a isotropic sphere, this magnetosphere. You also have a light cylinder where the plasma velocity can't, exceed the speed of light, right? And so this increases in radius as you go up from the surface of the neutron star. And so you have these cones, around the magnetic axis where the magnetic field lines can't reconnect. And so this is where the electrons are kind of getting accelerated, producing what's called curvature radiation as they travel along those open field lines. And then there's sort of this, the next part of the process is that those photons that are produced are triggering an electron-positron cascade that produces more photons. And we see this as sort of the pulsar's radio emission. It gets a lot more complicated than this when you're talking about sort of emission at other wavelengths. We talk about sort of emission coming from different gaps in the pulsar and things like that. But this is just a very simple picture of what's going on. Okay, so there are lots of things that happen to these pulses as they come towards us, right? So one of the most important things in terms of pulsar timing is that the ISM causes a lot of very interesting problems. We know that the ISM, this cold ionized plasma, it's inhomogeneous, it's changing all the time, it's turbulent, and so it's very difficult to model. And so sort of the most prominent of these effects is dispersion measure, and we'll talk about that next. But there are other things that happen too, right? There's diffractive and refractive scintillation, like stars twinkling in the night sky, right? Except this is with ISM. This causes flux density changes. There's also scattering, which causes kind of a general pulse broadening that's frequency dependent. It's usually proportional to the frequency to the -4. This is just caused by multi-path propagation, right? Some rays having to take longer paths than others. And it can cause this extremely prominent broadening at low frequencies. Okay, so dispersion measure, we don't need to go through the derivation of it. But the point is that this is an integrated column density of electrons along the line of sight pulsar. And the reason this is really important is because it causes a sweeping in our pulse, because lower frequencies are going to be delayed more. And it's Newton -2 is the dependence. So you can see on this last slide, this is sort of what an undispersed profile will look like. You see it as this sweep in frequency. And so this is a really simplified cartoon of what's happening. You have this delay that's affecting low frequencies more. And if you tried to sort of build up your pulse profile, if you're integrating over all these different frequencies, you would get something very messy. The pulse would be totally smeared out if you didn't do any dedispersion. And so what you have to do is you have to go through the process of kind of aligning all these frequencies based on the measured DM. And then you can integrate up the pulse profile and you get a nice clear pulse. But it's more complicated than that because dispersion measure is time dependent too. But one really nice thing about it is that it can be used to estimate distances to pulsars, right? There are lots of kind of galactic ISM distribution models that help you estimate distances to pulsars based on their measured DM to like 30% accuracy, something like that. And so there's a lot of work that goes into this. Pulsars are sort of, I think it's important to know that they're sort of uniquely suited for ISM studies, right? You have these nice point sources that can kind of be studied very well, can be timed very accurately. And that really helps you probe the ISM in a way that very few other kinds of studies can. Okay, so how do we actually study these things? They're fairly weak. We really need sensitive radio telescopes, right? So there are a lot of applications of radio astronomy that are very dependent on having good resolution. Pulsar timing arrays, pulsar timing in general isn't quite as dependent on that. We're fine with having just large, we just need light buckets basically. And the bigger the light bucket, the better. These emit at very low frequencies. They have super steep spectra. And so that means that we are observing at kind of unusually low frequencies. This is something like, a couple hundred megahertz to a few gigahertz. Excitingly, actually, one thing that's happening right now is that they're testing out at the Green Bank Telescope in West Virginia, which is a 100-meter dish. They're testing out an ultra wideband receiver that's going to span sort of this whole frequency range of interest, which is going to be really great for us for several reasons. But yeah, on the left, it's just a few examples. Green Bank is on the top right. There's Parks in the middle left. Arecibo, which unfortunately you probably know, collapsed in December of 2020. Our collaboration was that I'll talk about later, was very dependent on Arecibo, and it was a really amazing instrument. There's also this really incredible instrument called FAST in China. I know I changed I stretched it out. It looks bad, but I thought it was really funny because FAST is so big. It's a 500-meter diameter dish. Anyway, so Pulsars can be studied outside of just low frequency, kind of the radio regime. We study them using X-ray and gamma ray telescopes as well. So NICER, the Neutron Star Interior Composition Explorer, is an X-ray telescope mounted on the ISS. That has been really interesting, especially for probing the neutron star equation of state, which is sort of the purpose of the instrument. There's also Fermi, the large area telescope on Fermi, which is a really great gamma ray detector that's been up for more than a decade now. So the last thing I'll mention here is just that Jocelyn Bell-Burnell, when she was looking at the strip chart recorder output, was able to see pulses, right? And that's how pulsars were discovered. But unfortunately, that's a very atypical situation. You know, the first few sort of brightest pulsars might be able to be seen this way. But in general, you have to fold up the pulses modulo the known pulse period in order to really build up a clean, strong profile for a pulsar. So for millisecond pulsars, you're averaging over thousands and thousands and thousands of pulses for these observations. And so you can see this is like a 600-second observation on the y-axis. This is phase. It's just two rotations are shown here for clarity. And this is kind of a nice, bright pulsar. Okay, but why do we even care about pulsars? We care because they're space clocks, and that's really, really important for a whole lot of reasons. They're responsible for some of the most accurate measurements, timing measurements possible. They're comparable to atomic clocks when you're talking about measuring them over long time spans. This is actually really out of date. I should have updated this slide, and I apologize, but this is an example of like how well you can measure the pulse period of a pulsar, right? So 1737 is, not particularly special, but it has a period that's very well known, and this is very typical for all of our millisecond pulsar timing measurements. And so I keep mentioning pulsar timing, but now it's time to talk about what pulsar timing actually is. Okay, so pulsar timing in the most basic sense is just modeling each and every rotation of a pulsar. And you can see from this diagram, if the pulses just arrived at these very predictable sort of regular times, it'd be fairly easy to put together a timing model. But the reality of the situation is that all of these different delays and sort of interesting effects that happen to the pulses as they come towards us make the modeling a lot more complicated. And so it's more like sort of what you see in the middle. This sort of regular pulsating model isn't going to cut it. So pulsar timing is describing the process of kind of iterating and creating a model that can account for the arrival time of each of the pulses and also predict them, have predictive power pretty far into the future as well. So we're going to break it up sort of into two steps. One is extracting the actual time of arrival measurement of pulses. And then the next one is the process of actually fitting the timing model to these TOAs, the time of arrival measurements. Okay, so this is just going to be about how we kind of come up with TOAs, how we extract them from our data. As I already mentioned, you have to fold your observations many times modulo the pulse period. And so you can have, you create a template basically, that's this very clean representation of the pulse profile. And it's usually made from many, many observations. It doesn't have to be, but it usually is. And so it's sort of like representative of what the pulsar's pulse looks like at some frequency. And so what you're going to do to determine this delay is you're going to cross-correlate the template and the observed profile. This usually happens in the Fourier domain, and you find where that cross-correlation is maximized in order to determine the phase shift between the template and the observation. So where that correlation is maximized is giving you the difference between the kind of nominal phase and your observed phase. So you can see in the image in the right, this template profile is nice and clean. This is the red line. I think that, yeah, the left is 1600 megahertz data. The template was derived from 1600 megahertz data with the GBT. On the right is a lower frequency observation. So, you have this template that has been smooth. It's kind of noise-free, right? But then you are doing the cross correlation with relatively noisy data. But what you end up with is sort of a nice, in theory, this sort of nice flat distribution. But you can see if you, for example, use a template that's from the wrong frequency, because we know that pulse changes, pulse profiles change as a function of frequency. You can do really bad template matching if you're choosing the wrong template. And so that's sort of critical. This is what's happening when you're using the 1600 megahertz template to fit 750 megahertz data. Okay, so if you multiply that measured phase difference by the known period, the instantaneous period of the pulsar, you get a time offset. You add that time offset to a nominal point on the template. This is, often the edge of the profile, the start time of the observation, and that is your time of arrival measurement. And so this is a little bit of a detail. You often add an integer number of turns corresponding to about half the observation. So you're kind of getting the TOA in the middle of the observation. So the precision with which the TOA can be measured is dependent on a whole host of things. It depends on the signal noise of the observation, right? It depends on the telescope's gain, which is sort of like a sensitivity. It depends on the duty cycle, how much of the one turn is the pulsar on. You want it to be very sharp in order to do this cross correlation well. It depends on the period. Faster pulsars are measured better. How long you observe it, and the bandwidth of your observation. So anyway, kind of high precision timing is what we're interested in PTA work. And so we have to think really carefully about kind of minimizing and maximizing all these different components in order to be able to extract the best TOAs. And so pulsar timing basically works because the number of turns, the rotational phase difference between any two TOAs has to have an integer number of rotations. And so that's kind of like the binding fact. That's the limit. And so, for example, this is the phase as a function of time. We're able to measure the frequency and the frequency derivative of basically all pulsars that we're timing. And so we know that at two different TOAs, that has to be an integer number of phases, an integer number of turns. Okay, so before that can actually be determined, though, there are a lot of corrections that have to be made to TOAs, and it's a very sort of messy process in a lot of ways. One of the things that has to happen is transforming the reference frame to the solar system barycenter to get an inertial reference frame. You have to account for lots of delays that happen, sort of GR associated delays that happen both within the solar system and at the pulsar, especially if it's in a binary system. You have to deal with observatory clock corrections. So some observatories, or almost all observatories, kind of have to publish these corrections to their observatory clocks as compared to GPS. And so that has to kind of play a part in your pulsar timing, and it can make a very big difference, actually. And it can get very messy. You have to correct them for DM, as we talked about, and a whole host of other things. But basically, all I'm trying to illustrate here is that the creation of a TOA is not just as easy as the template matching, right? You have to do a lot more after that, too. Okay, so this is sort of on to the second part of pulsar timing. As we talked about, a lot of different things are going to dictate when the pulse actually arrives. We know that the pulse period derivative, sort of where the pulsar is on the sky, Keplerian parameters if it's in a binary, right? Even some general relativistic effects if it's in a binary under certain conditions, dispersion, all of these things are adding to the timing delay. And we call this difference between what the model is predicting and what we actually measure a timing residual. And so this is a very important sort of currency in pulsar timing. And you can see how kind of messing up any one of these factors can have a sort of dramatic impact on your residuals. So you expect if you have a very good timing solution, that's what you're seeing on the top panel here. This is a fast pulsar with pretty good timing precision. The residuals are going to be scattered around zero very nicely. You're not seeing any structure. You're sort of not seeing anything obviously wrong. If, on the other hand, you just have a problem with your spin down rate for Pulsar, for example, you'll get this quadratic effect in the residuals. If you have a problem in the position of a fairly small amount, you'll see a sinusoid with a period of a year, right? Kind of inducing this sinusoidal structure in the residuals. If you're getting the proper motion wrong, you have that same sinusoidal pattern, but it also increases over time. And then, if you have things like an object orbiting your pulsar, that can induce other kinds of sinusoidal variations as well. But what we're trying to illustrate here basically is that structure in the residuals basically means that there is an issue with your timing model. But I think it's a very interesting thing to look at, actually. Kind of cool to see how these individual factors in your timing model can induce that kind of structure. Okay, some sort of more advanced details here. The actual fitting of the timing models is usually using just chi-squared minimization, but there are a lot of new techniques that are sort of being used more prominently. One is MC-MC fitting techniques, and I think I have a slide about that later. The other thing to note is that these timing models are more than just like period derivative DM, right? There can be hundreds of parameters, especially in the timing models that we use for pulsar timing array work. One example of this is that in the way we currently model DM, it can bring in hundreds of parameters into our models. So it can get a bit messy. It's not super straightforward. I'll also very quickly say that there are different ways to extract TOAs. Usually the kind of normal way, which we call narrowband timing, is subbanding the data and extracting a time of arrival measurement from each of those subbands. But that means that you get, in this example, which I just drew by hand, you're getting 11 time of arrival measurements. And that the TOAs are sort of your data set, right? Instead, you could use this wideband timing technique that's been sort of in use for a while now and becoming a lot more popular and necessary. And so wideband technique is basically getting a simultaneous measurement of both the DM and a single time of arrival measurement. And this is really important as our data sets get longer and as our telescopes have more and more bandwidth. So you can see here, or rather, a good illustration of this is just that for Nanograv, which is the North American Pulsar Timing Array Collaboration. I'm not sure how much you've talked about the various PTAs, but in Nanograv, our 12.5-year data set, the data volume was reduced by a factor of something like 33 when we used wideband timing techniques versus narrowband. So this is sort of an important development that's happening in pulsar timing. Okay, so what does a pulsar timing array data set actually consist of? This is where we're going to start getting a little bit into the weeds. I hope, yeah, we're doing okay on time. So we have these files called .par files. They hold basically the best fit parameter values for each pulsar. You also have a .tim file, which holds the actual timing currency, the TOA measurements. And so that includes like the observatory, the actual time of arrival, the error on that measurement, and a whole host of other things having to do with kind of the observing setup. We also often include DM time series. So in the case where you're using DMX, you can see in the top panel, kind of this is an epoch to epoch measurement of the dispersion at that time. And so DMX is a model that you have some nominal DM, and then you're making epoch measurements of that DM. And so you can see how the DM changes relative to that nominal value over time. And it has this structure, and we'll talk about that a little bit later. You can see actually 1713 is sort of, I picked this because it's famously got a pretty weird DM time series. You can see that there are these strange drops, and these are due to sort of events happening in the ISM. You can also see here are sort of the pulsar timing residuals. You can see how well the pulsars modeled over long time spans. There are averages and whitened residuals and things like that down here, but that's not quite as important. For Nanograv and, for Nanograv as of right now, we also are releasing wideband measurements in addition to the narrowband pars and tims. We're also concerned about releasing versions that are compatible with different kinds of timing software. And so there are sort of traditional Pulsar timing packages that are still in very, very wide use, called Tempo and Tempo 2. But there's also a new one being developed that I think I'll talk about on a next slide. Yeah. So for nanograph specifically, our 12.5-year data set was the first time we released that wideband data set simultaneously with the narrowband one. And as I mentioned, the data volume was much lower. We're currently working on the 15-year data set. So you can see this plot shows with each successive data release how many pulsars we've added. It also carries frequency information based on color. It's a little bit hard to see. But the 15-year data release has 68 millisecond pulsars. So it's adding a lot, right? We had 47 the 12.5-year data set. So that's a really, really big leap, especially compared to differences in other data sets. We are adding VLA data. VLA is the very large array. I did mention that interferometers aren't necessarily necessary for pulsar timing array experiments, but the VLA is really great in that you can do high frequency observing. And so we'll also be able to reach far enough south that we're including data for a source called 0437, which is a very important PTA source. We've been working on totally overhauling kind of our workflow for at least the timing component of our analysis. I'll talk about that. And part of that overhaul includes the use of a new pulsar timing software package called PINT, which stands for PINT is not Tempo 3. There's a reference paper if you're interested in looking at it. PINT is very interesting. It's a really nicely modular software package. It's very well documented, very well tested. Tempo and Tempo 2 are like classic, extremely important software packages, and having people use two different software packages that were developed totally independently is actually very important for validating results, right? So the existence of sort of these independent software packages for pulsar timing is quite critical. But we've been using PINT within Nanograv at least, but we are really seeing both tempo-based results and PINT-based results, as well as a narrowband and wideband data set for this 15-year data set. And I think that you're going to be talking about using PINT in the demonstration, which will be really, really great. Okay, so IPTA data sets. I'm sorry if I'm repeating stuff. I'm not sure exactly what you've talked about so far. But the IPTA is the International Pulsar Timing Array. It's a consortium of consortia. It consists of a bunch of different pulsar timing array collaborations all over the world that are all sort of operating independently. But when we combine all of our data sets, we will improve our sensitivity to gravitational waves significantly. But this process of combining a bunch of different pulsar timing data is very complicated. It's a very interesting puzzle, but it can get a little bit overwhelming. But it really is sort of the ideal way to do our science. So in the IPTA second data release, it consisted of data from the European Pulsar Timing Array, which is 42 millisecond pulsars in that data set, the Parkes Pulsar Timing Array in Australia, plus their extended data set. I think the original has 20 millisecond pulsars. And then the Nanograv 9-year data set, which is several data releases ago, but has 37 millisecond pulsars in that data set. There's obviously some overlap because we're not seeing totally independent places in the sky, right? But the total number of MSPs is 65. And it's very interesting because all of the pulsar timing arrays have access to really incredible instruments and sort of go about their timing in different ways, but not anything that's completely different in nature, right? The differences are more in details and in sort of cadence and how much telescope time you have and things like that. But it's really good because it means that you sort of get this very diverse data set with different kind of cadence measurements on certain pulsars, having access to some pulsars that some telescopes don't have. And so it's a very powerful sort of data combination. Okay, so I mentioned the noise budget, and this is basically how we are characterizing all of the noise in our detector, and our detector is the pulsar, the array of pulsars, right? So pulsar timing arrays need this really incredible timing precision, right? Less than a microsecond. And that's pretty hard. it's not impossible, obviously, but not every pulsar can give you timing precision that good. And so, we have both white noise and red noise processes. These white noise processes that are sort of dominant on shorter timescales include instrument noise, radiometer noise, as well as pulse jitter. So you can see in this plot on the right that pulse shapes, individual pulses, are actually quite variable. But once you're integrating all the pulses, you get a very stable pulse profile. But there's also red noise, and so red noise can include things like there's both achromatic and chromatic red noise. Achromatic red noise over long time spans, right? It kind of causes this coherent drift in timing residuals. This can be attributable often to spin or timing noise, which is just something intrinsic to the pulsar. It's probably due to irregularities in how the pulsar rotates. Which I know is a very vague thing to say, but it's sort of a strange phenomenon. There's also chromatic red noise, and this can be DM variations over time, which we already talked about. We deal with these using white and red noise parameters in our timing. This is important both for the kind of timing working group and for detection, obviously. And I don't want to really go into the details of how these are all parameterized. We can talk about it if you're really interested. Okay. So this is what Nanograph has sort of been up to. The Nanograph timing working group specifically has been up to for the last little bit, sort of between the 12.5-year data set and the 15-year data set. And it is creating a pipeline called timing analysis, very creatively named. And the point of this timing analysis pipeline is to have a kind of reproducible, well-documented, clear kind of beginning to end timing process for each of the now it's something like 80 pulsars that we're timing. And so this is really important because it's also, it makes it more accessible for new timers, for students, but it also makes it very clear to other scientists and the public that we have this kind of reproducible pipeline in place. And so there's another part, which is in the same way we talked about how timing can kind of be split up into the TOA generation and the actual model fitting part. TOA gen is another kind of pipeline we have that actually deals with going from raw data to TOA measurements, but then timing analysis takes over after that. And so we have set this up such that we have a single file for each of the pulsars, and it has both a narrowband and a wideband file, and it's in YAML format, so it makes kind of categorizing different kinds of information very easy for reading it in, reading it out. And so you can make certain adjustments to parameters, right? You can tell them where the TOAs are located, where the profiles are located, what parameters you're actually going to fit for, what kind of fitter you want to use, some details about TOA excision, things like that. And they also include change logs, which is very important because these change logs are going to hold a lot of information about exactly what choices were made in terms of the timing and why. Okay. So it's based on this, the pipeline is based on this notebook framework. And so it's really easy to set up a new run to do kind of automatic running of the pipeline. And the notebook generates a PDF output. And so this PDF output is really great because it kind of summarizes all the information. It kind of highlights potential issues, right? It's saying, hey, your noise modeling is absolutely wild. Like, why are you kind of needing this much white noise in the model? Things like that. It makes sure that, we don't need to go into the details of it, but it tells you kind of the chi-square value for the fit, making sure that the reduced chi-squared is close to 1, things like that. It literally highlights things in red when they go wrong, right? So in this case, because we're doing automatic TOA excision, it'll tell you if every single TOA from a certain data set is being cut. It also provides permanent documentation of sort of the software that's being used, because there are several different packages in use, and kind of does very strict versioning. Okay, and so here is sort of, we already looked at these residual outputs, but you can see that, in these PDF summaries, you have a summary of kind of the final timing model, divided into frequencies, into front and back end pairs. You also have the kind of last couple of noise runs to compare and make sure that the noise is stable over time. It also tells you about the automatic TOA excision that's happened. And so, for example, you have all these good TOAs, 87 or 83% of your TOAs are good in this case, which is great. But you have TOAs that are excised for a bunch of different reasons. Some are coming from low signal to noise observations, which makes the TOA very hard to measure. And actually, there's a very specific reason why we put limits on the signal to noise that's necessary in a certain observation to keep that TOA. And part of it is because the errors are actually on the TOA are going to be very underestimated if you keep a bunch of low signal to noise measurements. Yeah, so we don't need to go into all the details, but you're basically getting the picture that there are a lot of different reasons why TOAs need to be excised. And then sometimes there are TOAs that are bad that haven't gotten caught by whatever algorithm you're using to do your automatic excision. And so we've sort of put together you know, a tool for exploring the data point epoch by epoch, right? And so you can see in this case, this is the kind of integrated pulse profile, but this is a single channel on the left. And you can see that there is something funky going on here, right? Because obviously it's going to be lower signal noise, but it should look something like this integrated pulse profile. And it simply doesn't. There's maybe RFI or something going on, radio frequency interference, which is a big menace in pulsar timing data. So anyway, so we're trying to make it easier to explore our data, basically is the summary from this. Okay, so I said I would talk a little bit about some advanced techniques. One is just Bayesian pulsar timing. It has a lot of benefits over kind of normal chi-squared minimization. One is that you have kind of a better view of certain correlations between parameters in the kind of uncertainties that you're getting from the fits. You are able to implement priors because we have some physical information about certain parameters. Being able to put priors in place matters a lot. You can do thorough model comparison. There's a really nice paper by Sarah Vigeland and Michele Valsineri that sort of summarizes these Bayesian techniques for pulsar timing. PINT actually has an MCMC kind of fitter built in, which has been really great. It's been used for several different projects. The one on the right, you can see this is actually non-pulsar timing array related, but it kind of lets you visualize what's going on. And so this is what's happening when you're fitting for two post-Keplerian parameters in a binary orbit. These are the mass of the pulsar's companion and the inclination of that orbit. And so we know, because of kind of what we know about binary evolution of pulsar systems, that there is an expected mass kind of for the companion. We here are putting just a Gaussian prior on it. And you can see that the data really are informative. They're kind of reaching above the prior and not just filling it. The other thing is that you can put kind of a prior on the inclination of the orbit by putting in place a random or a rather flat in cosine I distribution. And so this is what it looks like in sine I space. You can see that it's also informative for this parameter. And the idea here basically is just that you're trying to measure the pulsar's mass very well. But I'm giving that totally without scientific context, so I apologize for that. We also can do chi-square gridding. So this is just gridding over different parameters. This has been really helpful for certain issues we've run into in the 15-year data set and for other projects as well. And one thing to note is that this is another place where the wideband timing is going to be really important. Reducing the data volume really reduces the runtime, the kind of computational requirements for work like this. It's kind of a different ballgame. Okay, and the last thing I'll mention is just high frequency timing. And so this is in many ways not related to pulsar timing array work, but it actually sort of is. So the problem with high frequency timing is that you don't get many photons from your observations, right? So even the brightest millisecond pulsar in gamma rays is giving you like just over a photon a day. And so you can't just kind of do normal radio folding techniques. We have this very special single photon timing technique in place. And it helps us get out solutions that are very similar to the solutions that we get in the radio. And this is also implemented in PINT if you want to play with it. There's more than 10 years of Fermi data. And so these gamma ray solutions, comparing them with our solutions from radio can be really helpful. One of the reasons is because there are no ISM effects in high frequency timing. And so that can be a nice comparison, a nice kind of informative piece of information. And it turns out that it's actually maybe going to be possible with time to create a gamma ray pulsar timing array, which maybe is not intuitively immediately obvious, but it's going to lag behind the sensitivity that radio pulsar timing arrays can have, but it is going to be possible, and I think that's really exciting. I think that's very cool. Okay, and here are my conclusions. So pulsar timing is accounting for every rotation from a pulsar. And because we can time them to very high precision, they're great clocks. We use them for pulsar timing array applications, for other studies, and it's just, pulsar timing is a very powerful tool. PTA data sets are, they comprise the best fit parameters for each pulsar, as well as the measured time of arrivals. Noise matters a lot in our detectors, right? There are a bunch of different kinds. There's noise over short periods of time, long-term coherent noise. It can be intrinsic, extrinsic. It gets a bit messy when you start talking about noise. Nanograv is working on building this timing pipeline that will be totally accessible. It's accessible to all of you now, but will be accessible to the public soon. And there are other kinds of interesting pulsar timing techniques as well that are really important, even if we're not currently employing them in many pulsar timing array projects. And so my dog hopes that you have a great time for the next 2 weeks, and I'm happy to take questions. Thank you. I'm not hearing anything. I'm not sure if I'm supposed to.
You were supposed to, but I was muted. Any questions in the room or online?
There's one question online from Jakomba.
Yes. So can I go ahead?
Yeah.
Thanks for the nice talk. So I had a few questions on the timing analysis pipeline itself. So you have a flag for the fit parameters, right? So when we do a normal tempo to PLK plugin timing, we actually look for the, for example, if you are fitting F0, then we immediately go to the terminal and then we look at the post-fit risk RMS, and that's how we do the traditional tempo to timing, right? So is there some user interface kind of thing in this analysis pipeline, or how do we select the fit parameters? So for if we have a small baseline, we don't fit for all the parameters, right? So something something to do. Can we do this kind of thing with the pipeline? Something.
Totally. I'm actually really excited that you asked this question because I could talk about this for a long time. So just to clarify for everyone, I'm not sure how many people have done kind of hands-on timing. There's several different ways you can do it. You can sort of turn parameters on and off in par files, and this is like the very basic kind of command line tempo fitting technique. You sort of have to manually change parameters, put in jumps if you have large kind of jumps in your data sets, things like that. But Tempo 2 has this really nice GUI where it allows you to kind of select and deselect parameters. This is really especially important when you're talking about timing newly discovered pulsars whose timing solutions aren't well known, because you're having to do more kind of fiddling. And so having a GUI to do that is the way many people do their timing. And so PINT actually does have a GUI that people have been working on very recently, very hard, because it's sort of known how important it is to have that. And so it has a very nice kind of comparable interface. And so you should check out PINT for sure. The pipeline timing analysis is based on PINT, but we don't, having that GUI isn't super helpful for us because these are very well-timed pulsars. We're not doing, the parameters that we're trying to turn on and off are not ones that necessarily will have an obvious, like a visible change in the timing residuals. And so we use other statistical tests to figure out whether or not we should include those parameters. So timing analysis itself does not have a GUI associated with it. It does have kind of a notebook, which is a nice thing, but not what you're talking about. But PINT does, so definitely check it out. Was that your entire question, I hope? I hope
yes,
I addressed every
yeah.
part. Okay, cool.
Yeah. Thank you. So I have another question. So if I can go ahead. So this is regarding the bad TOA. So so I understand SNR is one of the metric which you select for a bad TOA, right? But do you have like what if so the outlier is a genuine outlier because of some ISM phenomena or maybe some solar wind or something? How do you look at each and every profile, which would be hard, I know. So is there a metric to quantify that sort of thing?
Yeah, so that's an extremely good question. And the truth is that it's not really reasonable, as you already alluded to look at each and every profile. We do this automatic kind of outlier excision. You can do it based on a couple of different, many different algorithms that are all being explored. But however that auto excision happens, the TOAs that are flagged by the auto excision, we are making an effort to go back and look at the profile and make sure that there is sort of a physical explanation. But we don't necessarily do that for every outlier that's being flagged. We absolutely do that for every outlier that's tagged by hand that wasn't picked up by the algorithm, right? So for the ones where there's kind of a human element, we are being extremely careful about documenting the exact reason why, the profile looked bad because of RFI or low signal noise or something like that. But we are not necessarily documenting those reasons for every single outlier that is excised. And the kind of long-term effect of this is not really important, but I completely understand and sort of agree that the ideal situation would be looking at the data, right, from which each TOA was generated. And it's nice that we have the problem of that not being feasible because we have a lot of data, right? But yeah, we're not checking every single automatically excised outlier as of right now. I will also say that I didn't talk a ton about kind of how the observations work, but we have been working on, this is an effort by many people, kind of a pipeline that will take the observations as they happen, and the data is folded and everything. You can look at various things about the calibrations that happen during the observations, and so that sort of lets you do data assurance as well. In the sense that you can see kind of immediately if something's going wrong with your observation. And so that is another kind of filter that happens. But that's a really, really good question.
There's a question.
Yeah, it sounds reasonable. Thank you.
Thanks very much. Thanks for a really good talk. A little while ago, I was looking into doing some wideband timing stuff just with using the method in pulse portraiture. But we got hung up a little bit because the only way we could use it was using the piecewise DM, like the DMX method. I haven't really looked into PINT in over a year now. Has there been any effort to sort of put a more generalized DM version in that, or is DMX sort of the way in the future for PINT?
I'm sorry. So I could hear you up until the point where you said that you have looked at using pulse portraiture, and then can someone repeat what was said?
Oh, so sorry. I was just saying we were trying to do some wideband timing pretty recently, and we got tripped up a little bit because in pulse portraiture it seemed that we needed to use DMX, like the piecewise DM. I don't know. I've looked at PINT for quite a while, so I don't know if any effort has been put into making a more generalized DM version. But is that a plan, or is DMX kind of the way of the future?
Yeah, so that's a really good question, and I'm not sure of the answer. Kind of generalizing pulse portraiture beyond DMX, though. I don't know. I mean, with wideband timing, you still can kind of apply other DM models, but the way pulse portraiture is written right now sort of assumes the use of DMX, I guess. And so I don't know. That's a really good question, and I will ask about it.
Because it would be great to use some wideband stuff, but yeah, we're just confused on how to get up the DM version, I guess.
Yeah, absolutely. And if you want to email me, I can remember to ask about it. The truth is that the wideband timing is, you know, as I think you probably know, but just for context, it's only now becoming popular, and sort of the software that's usually used. People are only just starting to kind of learn how to use it and stress test it and things like that. And so it's still very much a nascent sort of technique. But absolutely email me, and I'm happy to talk about that.
Awesome. Sounds good. Thanks, though.
Other question?
Any other questions? Online or in the room?
I don't see any hands.
Going on? If not, let's thank Thankful again.
Thanks, everyone. I appreciate you having me.
Thanks, Thankful. So for everyone online and in the room, we have a 15-minute break, and then we come back with the time. So before the chat happens, just other people. Okay, so for the people in the room, so Steve just left to go to 2 meetings for an hour and a half. Hopefully he responds to my text. Panera's canceled our lunch order because they don't have enough food. So I'm gonna try to get a hold of Steve. He's just in the detection working group meeting, I think, right? So hopefully he can respond to a text and maybe find someone to cover it and come back because he has the money to pay for it. My initial thought is maybe just try to find a place to order pizza from. So does anyone have an objection to that? I know that a few people have food allergies, I think, like nut allergy, shellfish allergies, things like that. Hopefully pizza is sort of a safe option in that respect. But if anyone has any objections to that, just let me know. Otherwise, I think that'll be the fastest and easiest method and safest. And then I think the plan will just be, I'll just put it in the same Panera order for tomorrow. And hopefully tomorrow they'll fulfill it. And hopefully by getting it in early, we'll get to the bundle line. I think part of it is just requesting like an order for 20 people 2 hours beforehand. I just sort of got screwed by being late. So yeah, I mean they called me and I just didn't have my phone turned on. So we'll get food for everyone. Just maybe a little bit. Sorry about that. Yeah, chocolate. Okay, yes.
They were already
Okay, so for this tutorial, I have a couple of notebooks up on the GitHub repository for the workshop. So if you come on to the Slack channel that we have, the PTA Summer School channel, there's this link that's printed up here that will take you to the GitHub page. And so if you navigate to V1, V2, and then timing tutorial right there. There's two notebooks in there, and then some data that's needed for a couple of images that are in the notebook. So if you all have already cloned this repository, make sure you fetch up Steve online, and then do a git pull locally so that you have these files with you. And then if you have all of your environment set up, then feel free to run these notebooks in the environment that you set up yesterday for this workshop. The first notebook that we'll be working through is timing underscore Libstempo underscore intro. So I will let's give this 5 minutes. If you run into a problem or a question, feel free to just shout it at any point in this computer. That goes for the people online as well. Just feel free to speak up because I can't really see the hands when I'm sharing my screen. So please don't be shy to speak up. You people have this notebook with them? Since you know you will be working, give it a couple more minutes. Okay, so it seems like everyone has the notebooks with them. If you do not have them or are stuck at some point, I can come over in a few minutes and try and help you out. But if you do want to follow along, you can still follow along just from the GitHub repository itself. If you click on these notebooks, you can just render these notebooks in your web browser. You just won't be able to run them. So that's another way that you can follow along if you're having trouble getting used to run on an issue. But so what I wanted to do with this tutorial is, rather than stepping us through the entire process of generating POAs all the way to deriving a timing model, I felt that that wouldn't be very helpful to people in the room, just because I feel like most of your interests lie with the gravitational detection side of things, rather than generating the data itself. I know a few people here are working on generating the data, and for you people, this will be either you will already know all of this, or this will not introduce too many new things. But I hope you'll still be able to take something out of this. Right, so Thankful already gave us an amazing talk about the process that goes into generating all of the DOs. You need to pull your profiles, you need to cross-pollinate them with the data that you observe on any given epoch, and then that sort of gives you your measurement of the time of arrival for any given epoch. You put all of those together, and that essentially gives you your TIM file. So your .tim file is a collection of all of the times of arrivals that you have for any given pulsar. And that is your data. What you need once you have a data is a model to fit that data with. And so the model is usually a combination of a lot of factors, most of which are summarized in this nice little flowchart here. So in generating this flowchart, the main focus has been sort of geared towards the detection side of things. So you can see I've absolutely not done justice for the timing model, where I've only listed sort of 4 of the major parameters that go into the timing model. But as we saw in Thankful's talk, it's literally everything that we have in the timing model, and most of the things that we have from the white noise part of it are actually coming to us from the process of generating the timing model. And the timing model is typically stored in the .r file. So these parameters usually come to us from at least the nanograph from the timing voltage group. And when we are doing GW analyses, we sort of assume that as the truth, and then work our way starting from there. So when we're doing these GW analyses, we rarely, if at any time, actually look at the residuals themselves. So over the course of these 2 notebooks, I just want to give you a feel for what the residuals look like, introduce you to some basic functions in both Libstempo and PINT that you can use to load in these timing models and your POAs, and then plot the residuals given the timing model that you have from your power file. And then particularly in this notebook, we will sort of go through and see how changing or having one model or having one parameter incorrect in your timing model, how that would affect your residue. We saw a little bit of that on one of the slides that Thankful had, but I sort of wanted to step through that again, but this time in just a more hands-on fashion, so that you can work with Libstempo as well. So Libstempo itself is a software package that was originally written to be a wrapper around Tempo and Tempo G. So Tempo and Tempo G are, for the most part, run from the command line for the terminal, and there exist wrappers around in Python that you can use to sort of read that data into Python and work in Python environment. PINT is obviously the next sort of step in that direction, where everything is natively Python, including the timing software itself. So what I would like everyone to do is sort of go through this notebook, make sure you read everything that's written in all of these cells, go through all the steps. The code in there has for the most part already been typed out for you. And some cells have also been done, so you will also have the output in front of you. But I would recommend you go through this notebook, run everything, see how things work, see what functions you're using in this tempo, try to understand why things are happening the way they are. All of these things and all of the effects that we're looking at have been quite well explained in the deck that's around the particular code cell. And yeah, and I'll be walking around the room and seeing if people have questions. And we can chat at that time if you want. Ideally, I would have liked to do this as sort of a coding exercise where we would go through all of this together. But given that we don't have enough time, I feel like this would be a better way to go about it. And you will also have all the code available with you so that you can go back to it later on, if necessary. So let's give this about 30 minutes. So we catch back up at 12:05 at the latest, if not sooner, if people are done stepping through the circle. Yeah, so feel free to start going through the notebook and be walking around. Shout at me if you have questions, both in the room or online. Yeah.
I mean, it's probably not gonna be I precise Pulsars. But, you know, concept.
Well, because I said even like the item that I said it 1%.
Well, we can always be sorry. So one of them is that you can't find the utility or not. And then you can find there's an issue that's executable or you can find
Like I can import it when I'm actually inside of like inside of Python in my actual in my terminal, but I just can't do it when I set it as a wall. I can.
Yeah.
It looks like.
I'm not entirely sure.
The error that we're getting is that this environment is not dead. Which is why I tried this.
Yeah. 71 hours.
Yeah. That makes a lot more sense.
532. So 480 seconds version 532. L3 filter, then 5 seconds version 209 for L3
Because I would,
filter.
so as a.
Outward scope.
So we're trying to do it on the Jupyter environment.
Running standard sample is like 40%.
I assume that you threaded it out.
So just imagine what's the actual.
Yeah, so downside is actually pretty.
So what's
There's a couple of things.
Yeah.
Probably,
You know, like. The you have an environment.
Yeah,
That was really good to do. That's also make it much more transportable.
yeah, so that's why he did that, with 6 megabytes. So if he hadn't fallen,
Oh, yeah, no.
he would not get that.
So it's
Yeah.
right here, and again, the sense that people have to move it on all of the. Any questions so far? Yes.
I'm a little curious about, so for the example that was the F-bomb example where the F-bomb is wrong, I'm a little curious what causes, the shape of that, why the shape is what it is, basically.
Yeah, so if you have your F dot wrong, then what that essentially amounts to as time passes on is an error in F0. Right, so your F1 is essentially your df over dt. So you need to be correcting your F0 as time passes on. So as time's going on the x-axis, you have your period just that much wrong. And so what you're seeing is sort of a slow moving effect of something like this, where your period is not instantly wrong, but it's long over wrong. It's wrong over long duration. And so you kind of see that effect building up. Eventually you'll hit the point where you're going to hit this what's called phase damping, where you just be so wrong that your observed profile that you're trying to cross correlate with will just jump to the other side of your phase damping.
So it's the same effect as this, but slow. Well, it's also quadratic, right?
Yeah.
So with F1, you've said it's 10 to the minus 19. Do you get any problems with flow accuracy with Python or whatever? Is it Fortran that is written in? That tempo was originally written in.
So tempo 2, I do not know, just because I'm not familiar with the source code. I think for Libstempo, it handles this internally, like it chooses the right data format for all of these variables that your DOA, without actually telling you about it. So it does that behind the scenes. In PINT, you can actually explicitly tell PINT that this should be a long double row with like a float or something. But it's essentially handled behind the scenes. But eventually you do run into like precision issues that you need to worry about when you get to precision. Cool.
So I think that Libstempo, when you're evaluating the model and things, it just calls tempo 2, basically, you have the scenes, right?
I've heard different things from different, like Libstempo has its own figure. So I don't know.
It does, but I think that you still call the model to generate the predicted model at each time. I think you still call that for tempo 2.
Yeah, I think that, yeah, that's right. Yeah. No, I think that makes sense. So Libstempo definitely uses tempo 2 to make sense of the timing model. That's for certain. But then fitting it is more ambiguous, like what it's doing. Other questions?
Nihan, can you hear me?
Yes.
Yeah, so I was wondering how can we get the covariances using this PSR.fit? Can we get that when we fit?
Sorry, could you say that?
Can we get the covariances when we fit for some parameters here using PSR.fit? So just like we get in the tempo 2 terminal, right? So
yeah, that's a good question. I want to say yes, but I don't know what the method is off the top of my head. But do you know what the method is to get covariances?
The method for covariances in
Libstempo.
It calculates the design matrix. It just uses the design matrix. I think again the tempo 2 outputs.
Yeah, but is there like a one-line method call that you can do?
To get the design matrix
Or
or
covariance?
oh geez. I don't know. The covariance matrix should be some combination. The covariance between the parameters, you mean? Yeah, it should be some. I don't know. Yeah, sorry.
I don't remember the method off the top of my head, Jack. I can look it up and we can connect on Slack about this.
okay, sure. Thank you.
I think it depends on the fitting method, right?
I honestly don't remember.
Okay, yeah. So I think if you have like derivatives, you can, with the whatever fitting method you use, you can generate covariances. But Libstempo, you also.
Yeah. So I was just asking because in tempo 2, sometimes many times when we fit, when we do all sorts of fitting, there is a covariance warning, right? So in the terminal that we see here, how do we get to know about it? So
Yeah, no, that's definitely a good question, and I'll try and find out how to get it in Libstempo.
Yeah, so for the one where we changed the problem motion for the RA, I understand why it's sinusoidal, but I was kind of curious as to why it's increasing linearly. I believe that is linear, right? Not exponential.
I think so.
Okay.
Yeah.
Yeah, I was just wondering why is that happening, and would it also have like a phase wrapping thing if we went on for longer?
No, it won't produce a phase wrap because this comes down to in which order you apply these degrees. So phase wrapping comes from trying to calculate the absolute phase of the pulsar. So if that's correct, which is spin down and you spin period, then that stays fine. But the position and the proper motion come from astrometry. So what's happening here is that you know exactly well how your pulsar is spinning. But what we don't know in this case is how fast it's moving across the sky. Yeah. So when you start out at time 0, it looks fine. And once you go out to like a year, you can see that as it's moving on the sky, your position is just getting that much worse as a function of time. And so once you expand that out in time, it just gets progressively worse. So your delays are sort of adding up because you're not correctly accounting for the pulsar motion. Right, so that's why it's sort of expanding linearly. I actually don't know if it's linear or if it should be exponential, but that's why the amplitude of that sine wave is increasing. And the reason why it's not a phase wrap is because this is an astrometric effect rather than like an absolute phase.
Okay, thanks.
So with the proper motion, like this assumes that the proper motion is completely constant throughout time. Is there any way to deal with it if it's not constant? Or is that just not?
So you can model for variations there. You can add that to your timing model. But that just comes down to a question of model selection. It's whether you can detect it or not. It's
Right.
not whether it's that, because nothing is moving at like a constant speed.
For sure.
It's just whether it's strong enough to actually affect your timing at a certain level that you actually need to worry about.
For sure, for sure. I guess I was just thinking like if you weren't trying to use it for like gravitational wave measurements, but you're actually trying to get the proper motion over time.
Yeah, so that these kinds of questions become super important when you're dealing with things like globular cluster pulsars, where they're not just moving like normal field pulsars, but they're also moving in the cluster itself. So there, these kinds of problems become more important and you actually need to deal with them. So yeah, there's definitely cases where there's more emphasis on determining the problem and how it's changing. If there's no more questions, then in the last part of this tutorial, we're going to switch over to the second notebook called timing underscore point underscore introduction. So we have about 10 minutes left, given that we started at 11:20. So I'm going to sort of quickly walk through this notebook. We have some hard time later today, so feel free to run through this notebook at that time. If you're not working on anything else. But so PINT, like I said, is, or as the example said, is a software package that's completely independent of Tempo and Tempo 2, which have sort of existed forever in the world of Pulsar timing. And so PINT is completely Python based, and as a result, it follows all of the conventions that we find in Python. So all the objects that you create are class-based, and then you add components and parameters to a base timing model class that you can create in PINT. And so since this is essentially being built up from scratch, PINT looks a lot different from Tempo 2, though the developers of PINT are trying to add in all the features that Tempo 2 and Tempo offered in their respective packages. So PINT itself comes with a couple of example datasets, which are being used in this example notebook. So comparing this again to the Libstempo notebook, if you recall, in Libstempo, we typically initialize a pulsar using a command called tempo pulsar, but that gets replaced by a get model and GOA command in PINT. So right off the bat, you can see that PINT tends to be more readable, just because it comes from this Pythonic philosophy of you should be able to read the code that you have. So get model and GOA is sort of the default way in PINT to load in your timing model and your times of arrival. And you can print out your timing model n, which is what's done here. And here you can see that each parameter that's present in this time solution is given in its entirety. So you can see which parameters go into the calculation of absolute field. You can see which parameters contribute to going into the equatorial modeling or the astrometric modeling of the pulsar. You can see the dispersion parameters. You can see the solar system Shapiro parameters. So these are accounting for the Shapiro delay from the pulse propagating from the pulsar through the solar system people. Solar wind dispersion. So solar wind, I'm sure you all know, is just plasma that's emitted by the sun. And if you have pulsars that are close to the ecliptic, then that can actually produce noticeable deviation in the dispersion measure that we mentioned. So if you want, PINT has the capability to model the solar wind effect implicitly. And then you have your spin down model F0, F1. and then the epoch at which you're referencing all of these measurements to. PINT also has this tropospheric delay, so it accounts for any delays coming from the ionosphere around the Earth, and that's also something that's really nice. Another thing to note is that following the name of the parameter, which you can directly access through something like m.f0, for instance. I haven't done this song. To m.f0, and that will give you access to each parameter. We can do the same for each component, which is these things. And so each parameter given where its type is given by what's here on the left hand side is associated with a value and uncertainty, and then a flag for frozen. So if you set frozen to true, then PINT will not fit for that parameter when you're doing the model fit later on in the process. Whereas if frozen is false, then that parameter will be included in your fitting process. You can similarly print out the summary for the POAs that you have in the data that you're working with. So here you can see that this example has 62 TOAs in it, observed at GDP, and then this is the MJD span, and then other information about the frequency, then some basic statistics about the POA errors. This is how you would get residues in PINT. So these are, just to know, these are pre-fit residues. So this function by itself will not do a fit, but it will just return the residues given any model and any set of POAs. It will not try to optimize that model to get you the least high square fit for any kind of fitting that you want to do. So this will just take the model that you give it as is and then return the residues to you as is without doing any kind of fitting. This is just a quick example of how you can flag certain POAs. So here I'm flagging POAs that have, or I'm actually retaining the POAs whose uncertainties are less than 30 microseconds, and then the assumption that we sort of made the choice that anything with uncertainties greater than 30 microseconds is just representative of bad data in the system. I'm not saying this is representative of the real world pipeline, but this is just something for this example. This residuals function can then be used to access either the phase residues, so this gives us residues in terms of phase, or time residues, which is what we saw in Hansel stuff. So all the residues she showed, I believe, were time residues. And finally, here's the big one. This is the function in PINT that will actually do the fitting for you. So PINT has a lot of different fitting functionality available in it. You can do just the usual weighted least squares fitting. You can do generalized least squares fitting, which is needed when you have correlated uncertainties and things like that noise. That's when you would need the generalized least squares method. As Thankful said, it also has an MCMC fitter in it, which is based around the package MC in Python. And you can make, if you know what you're looking for, you can directly use that fitter. But if you don't, you can then just use .auto and then PINT will determine what fitter is best for you, given the data that you've given. So in this example, it tells that for narrowband POAs without correlated errors and downhill fitter, just return this kind of fitter, and it does the fit with that type of fitter. So this is just plotting some of the statistics, which can easily be accessed through the instance of the fitting class. So we can see that we have a really nice solution here, so that reduce chi-square close to 1. You can get f.print summary, which will print out, which will give you essentially what it says, a summary of the fit that it has just done with that PINT fitter, and it will show you the pre-fit parameters as one column and the post-fit parameters as the second column. And I don't remember if this was on one of Thankful's slides, but We have something that looks like this in the nanographic linear timing pipeline as well. So this gives you like a one-page review of all the changes that might have happened in the fitting process when you're getting new solutions or updating solutions for any pulsar in your dataset. This also gives you a list of some derived parameters. So things like if you have the frequency in your power file, it will instead give you the PA and the PA dot. It will give you things like characteristic age, surface magnetic field and light cylinder, and then the spin down E dot. So the energy that's being immediately generated by pulsar. So the fitting instance itself will also give you access to the timing residues or the phase residues, which you can then use to plot your post-fit residues. So in this case, since we know the fit was really good, it had a reduced pi squared of 1. We see that the residues are looking sort of Gaussian distributed around 0. So essentially what all that's left is random Gaussian white noise in the data. Right, and this cell is just to show the contrast between the data that we decided to excite and the data that we kept down for the actual fit itself. So just to quickly summarize the way that you would create a timing model in PINT is that you would follow the Pythonic way of sort of working in class-based instances. So in PINT, you can sort of take a top-down approach where as the first step, you would create an instance of the timing model class. And then once you have your timing model class set up, you can then populate it with different components. And then to these components, you can then add in the parameters after that. So you have this piecewise recipe of constructing any timing model that you would want for any of the pulsars that you're looking to time in your favorite PTA. So we are close to the end of this session. So I'm going to stop there, but all the code below this part of the notebook essentially will walk you through the different types of components that are available in PINT, and then how you can add them into your timing model instance, and then how you can add in parameters. You can pass them in as a dictionary, or you can pass them in as specific variables by getting the attribute from the timing model, and then setting up and validating your timing model. And then finally adding in individual components that you might want to add on after the fact. So let's say we have a timing model that we've already started out with, and then we want to add or remove parameters from it. The last part of the notebook will sort of walk you through the process of doing that. Right, so apologies for running out of time here, but please step through this notebook whenever you have the time. If you have questions, I'm around for all of the 2 weeks, or find me on Slack or email. And a lot of this code, well, almost all of this code was borrowed from the PINT documentation, which is very thorough and exhaustive. So if you want to dig deep into anything that's in the notebook, feel free to go through the documentation. And if you would like to get involved in PINT development because it's still being actively developed, then if you don't know who to reach out to, let me know, let Steve know, let someone know, and we can direct you to the correct meeting. Right, so that's all I had. Are there any questions before we break for lunch? Okay, if not, then let's break for lunch, and we will meet back at, what is it, 2 p.m. local time. So in about an hour and a half. So yeah, I will be done.
So food, well,
Oh, okay.
supposedly 1 o'clock, but according to the website, they haven't started prepping orders yet.